Hi everybody, this is our lecture on section 5.5, triple integrals in cylindrical and spherical coordinates. So first we'll do cylindrical. So given a 3D region in the following form, A less than or equal to R less than or equal to B, alpha less than or equal to theta less than or equal to beta, and then pxy less than or equal to z less than or equal to qxy, like that, a region R of this following form, then the triple integral of whatever function you've got, f, x, y, z, dv over r, is equal to, well, we did this already, actually. Right? It's the integral from pxy to qxy, fxyz dz. So x and y are held constant, and then you integrate with respect to z with boundaries, constant boundaries, pxy and qxy, because x and y are constant. But then after that, you proceed, r dr d theta, you proceed by polar coordinates. So you do a triple iteration, an iterated integral, triple iterated rather than double iterated, right? Iterated. And the first iteration is with regard to the rectangular coordinate z. Right? It fits in very well with cylindrical coordinates. And then the second and third iterations are with regard to polar coordinates. So we really already did that in the last section. So now we're just sort of formalizing it. So, for example, so we had an example in the last section, in section 5.5. I forgot what number it was. But here's another one. So take the sphere of radius 2. X squared plus y squared plus z squared equal to 4, centered at the origin. Inside the cylinder of radius 1. And that is x squared plus y squared equals 1. Centered on the z-axis. So let R be a region above the xy plane. Right? In other words, z bigger than or equal to 0. Inside the cylinder, and below the sphere. So how's that going to look? So here's your x and y axes. And on top of this, we've got that smaller part of the sphere. Right there, like that. So this is our region R. All right, we've got the sphere, that little cap of the sphere on top, and then underneath that and inside the cylinder of radius 1. So integrate, calculate. Oh, well, so how would we describe this in terms of spherical coordinates? So in spherical coordinates, R is equal to, well, the radius goes from 0 to 1. The angle goes from 0 to 2 pi. And z goes from 0 to this top half of the sphere. All right, and that's x squared plus y squared plus z squared equal to 4. So 0 is less than or equal to z is less than or equal to square root 4 minus x squared plus y squared. All right, so that's the description of this region in cylindrical coordinates. So now let's calculate the following triple integral. The triple integral of 1 dv over r. And the triple integral of 1, it just gives you the volume of the sphere, which is equal to the volume of r. Just equal to the volume of r. So let's do that calculation. Okay, so the triple integral over r of 1 dv in cylindrical coordinates is the integral from 0 to square root 4 minus x squared minus y squared, 0 to 1, 0 to 2 pi of 1 dz, and then we use polar coordinates after that, r dr d theta. So we reduce the triple integral to a double integral by first iterating with respect to z, and then the double integral that's left over, we integrate with respect to polar coordinates. So the dr and d theta have this extra r, that correction factor there, or transformation factor. So antiderivative of that is z from z equals 0 to z equals square root 4 minus x squared minus y squared, r dr d theta. So this is equal to the integral from 0 to 1, integral from 0 to 2 pi, so then it's just equal to this minus 0. So square root 4 minus x squared plus y squared, r dr d theta. Now, of course, we have to transform this into polar coordinates now. You can't use x and y anymore. It has to be expressed in terms of r and theta. So here we just have, this is r squared, x squared plus y squared. So this is equal to the integral from 0 to 1, 0 to 2 pi, r times square root 4 minus r squared dr d theta. All right, make sure you transform x and y into r and theta. All right, so here we need a u substitution. So let's do it off to the side over here. So antiderivative of r 4 minus r squared dr. All right, this is 4 minus r squared to the 1/2. With u equal to 4 minus r squared, it cancels that out. Right, so this is 2/3 4 minus r squared to the 3/2, and then times 1/2, minus 1/2, I think, to correct for the 2 here. So that's minus 1/3, 4 minus r squared to the 3/2. That's that antiderivative right there. Let's double check it. So 3/2 times 1/3 is 1/2 times 4 minus r squared to the 1/2 times minus 2r. So the minus 2 cancels the minus 1/2 and leaves us this. Okay? So that's the antiderivative. Sometimes it clutters up the main calculation less if you do part of it off to the side, which is what I like to do myself. Because you want to keep the main line of calculation as uncluttered as possible. So, alright, so this becomes integral from 0 to 2 pi, 4 minus r, or minus 1/3, 4 minus r squared to the 3/2 from 0 to 1, r equals 0, to r equals 1, d theta. So it's integral from 0 to 2 pi at r equals 1. This becomes minus 1/3 times 3 to the 3/2. So minus 1/3, 3 to the 3/2. At 0, this becomes 8. Yes. At 1, so that's 3 to the 3/2 plus at 0, 8 times 1/3. So this becomes square root 3. So this is 8/3 minus root 3, integral from 0 to 2 pi, 8/3 minus root 3, d theta. That, of course, is a constant, so your final answer is just 2 pi times this. 2 pi times 8/3 minus root 3. Okay? So that's an example using cylindrical coordinates. And we've seen a couple regions in which, this has been useful. Right? There was the example, there's this one here. There's that example we did in class the other day where we had this region, if you remember. So this was that paraboloid upside down on the meeting the xy plane right there. So it's x-axis, y-axis, z-axis was here, and this was z equal to 4 minus x squared minus y squared. Right, so this region was 0, so the base of that region, if you took this region and squashed it down into the xy plane, you get this disk right here. And what disk is that? That is the disk, so z is equal to 0. Z is equal to 0, so we get x squared plus y squared equals 4. Right, so this is the disk of radius 2. So we have 0 less than or equal to r less than or equal to 2. 0 less than or equal to theta less than or equal to 2 pi. 0 less than or equal to z less than or equal to 4 minus x squared minus y squared. Right, so this was a region used in problem, let's see what it was. There it is. So that was before we learned about doing integrals in cylindrical coordinates, but we actually did use it. So that's number 198. 198. Let me present that separately. All right, so here is another 3D region that is perfect for cylindrical coordinates. It was used in problem 198. Section 5.4, problem 198. All right. Oh, excuse me. So spherical coordinates calculating triple integrals using spherical coordinates is great when you're talking about regions that are, spherical or, parts of the sphere that are, easily described using spherical coordinates. So some regions in 3D can be most simply described using spherical coordinates. So in case you're not quite remembering, in spherical coordinates, x is equal to rho cosine theta sine phi. Y is equal to rho sine theta sine phi. And z was equal to rho cosine phi. And what the meanings of rho, theta, and phi are as follows. You have a point in 3D space, and it has a distance rho from the origin. And so this is the point rho, theta, phi. If you drop this down to the xy plane straight away, and then you take this segment from the origin, so you're projecting the hypotenuse of this right triangle down into the xy plane and getting this leg of the right triangle. So that's a right angle. And this rotation from the positive x-axis is theta, and this angle of declination from the z-axis is phi. Right, so you have a distance from the origin, angle of declination, and angle of rotation. Right, where theta and phi are analogs of latitude and longitude, and rho is the radius of the sphere on which the point lives. So, like on the Earth, right, rho is always, right, it was 3,950 miles or something like that. Okay. So, some regions easily described using spherical coordinates. One, the sphere. the sphere of radius k and its insides. All right, this is 0 less than or equal to rho less than or equal to k. The sphere of radius k centered at the origin and its insides, of course. And its inside. So 0 less than or equal to rho, less than or equal to k. 0 less than or equal to theta, less than or equal to 2 pi. So full rotation of 360 degrees in the xy plane. And then, the angle of declination goes from 0 to 180 for the negative z-axis. So you only go from 0 to 180 for the feet, not 0 to 2 pi. 0 less than or equal to phi, less than or equal to pi, not 2 pi. Another region which may not immediately register as easily described using spherical coordinates is the following. The cone centered on the z-axis whose sides have declination alpha. So the inside of the cone so the region enclosed between the cone centered on the z-axis whose sides have angle of declination alpha and the sphere of radius k. So if you want to draw this thing, you're going to have this cone. The angle of declination from the positive z-axis is alpha. So this angle right here is alpha. And then topping that off is the sphere of radius k. All right, so this snow cone shape. Well, that's very similar to this. The only thing is that the only difference between this and that is that the phi only goes from 0 to alpha. Right? You're getting a full rotation. You're getting all the points rho from 0 all the way out to the sphere itself. So every point, every line from the origin that doesn't go beyond the cone every line from the origin that doesn't go beyond the cone hits the sphere. So those are just radii of the sphere of radius k. Full rotation in the xy plane, 0 to 2 pi, but then angle of declination is just 0 to alpha. All right, so it's almost just like the whole sphere. It's described very similarly. Okay, but there's, just constants used throughout all of this. All right, let's talk about how the integral is supposed to look in this case. So in this case, when r is described in spherical coordinates, okay, the triple integral over r of f x, y, z, dv is equal to the triple iterated integral, okay, with appropriate bounds, f, and what's x? Rho cosine theta sine phi. Y is rho sine theta sine phi. And z is rho cosine phi. And then what's dv? Well, it's not d rho, d theta, d phi. There's again a correction factor. It's rho squared sine phi d rho d theta d phi. Right? Or any other appropriate ordering of these points depending on what your bounds are. Okay, so here there's this correction factor, and that has to do with for integration in spherical coordinates. So there's that correction factor for the transformation from rectangular coordinates to spherical coordinates. It's right here. Just like there's a correction factor for the conversion from rectangular coordinates to polar coordinates, or rectangular coordinates to cylindrical coordinates, right? And that correction factor was just r itself, just r. And the form of this correction factor has to do with various aspects of what the volume of a sphere is, or the volume of part of a sphere, a spherical box, if you will. But I really don't want to get into that. That's kind of a bit much. So we'll just take that as known in this instance. Okay, let's take the following example. All right. So another region. So we had these two regions up here: the sphere itself and this snow cone. Let's take a little variation on the snow cone. So consider the following 3D region shown. So we'll again take the cone just 45-degree angles on each side. But instead of being topped by the sphere centered at the origin, let's have one that's not at the origin. So let's say, so again, this is the sphere. Z equals square root x squared plus y squared. So that's the, not the sphere, the cone. That's the cone whose sides are angled at 45 degrees downward. And here, this is going to be the sphere x squared plus y squared plus z minus 1 squared equals, let's just say 1. So that's the sphere of radius 1 centered at 0, 0, 1. So rather than centered at the origin. Now, even though it's centered at 0, 0, 0, 1, it can be described nicely using spherical coordinates. So this is z minus 1 squared, so we have, since it's the top half, z minus 1 is equal to, 1 minus x squared plus y squared square root, and then add 1 to it. Or no, let's not do it that way. Let's write it out this way. This is x squared plus y squared plus z squared minus 2z plus 1 equals 1, so those cancel. So we have x squared plus y squared plus z squared equals 2z. Okay, so that's nice because this just becomes rho squared. Remember, in spherical coordinates, right, x, y, z are these things, but then if you square all of them and add them, it just becomes rho squared. Right, so this nice relationship, much like what you get with polar coordinates. Okay. So consider the following 3D region. Let's calculate, again, let's just calculate the volume. Oh, so I'm sorry, this is R right here. So what do we have? We have, so this is rho squared is equal to rho cosine phi, because z is rho cosine phi. Cancel out one of the rho's on each side, and you have rho is equal to 2 cosine phi. So the edge of the sphere there is 2 cosine phi. So if you take any point from the origin, any straight line from the origin to that sphere, it's got this coordinate. Okay, rho, so theta can be anything, and then rho and phi are related by these numbers here. So we've got 0 less than or equal to theta less than or equal to 2 pi. Phi, well, the angle of declination for this standard cone here is 45 degrees, pi over 4. 0 less than or equal to phi less than or equal to pi over 4, and then 0 less than or equal to rho less than or equal to 2 cosine phi. So this is the description of R in terms of spherical coordinates. So we've got theta bounded by constants, phi bounded by constants. rho bounded by functions of phi. So in the integration, d rho, d theta, d phi, d rho, d theta, whatever ordering you have, rho must come before, d rho must come before d phi. Okay, because rho is in terms of phi. So phi must be held constant in order to do this integration, in which case d rho has to come before d phi. And then d theta can be here or here or here. Okay, because theta is just bounded by constants. So that can happen whenever. So here, what do we have? Oh, so now let's calculate the volume of R, which is just the triple integral of 1 dV. All right, so this is triple integral over R. 1 dV is equal to, boundaries are, let's do d rho first, 0 to 2 cosine phi, and then 0 to pi over 4 for phi, and, or that's for rho, I'm sorry, and then this is for phi, and then this is for theta, 0 to 2 pi. And we've got 1, which is just 1, and then the correction factor is rho squared sine phi d rho d theta d, or d rho d phi. I've got phi second, theta last. D rho d theta d phi. So we'll do the first anti-differentiation with regard to rho. So sine phi is a constant. So the antiderivative with regard to rho is 1/3 rho to the third times this constant, sine phi, evaluated from rho equals 0 to rho equals 2 cosine phi. D phi d theta. So this becomes integral from 0 to 2 pi, integral from 0 to pi over 4. So it's going to be 8/3 cosine to the third phi sine phi d phi d theta. Okay, so we want to do the antiderivative of cosine to the third phi sine phi. So that's going to need a u substitution. I'm going to do that off to the side over here. Okay, so antiderivative cosine to the third x sine x dx. All right, this is let u equal cosine x. So du over minus sine x is dx. So we've got antiderivative minus u to the third du. All right, the sine x cancels, pull the minus 1 out front. So you got minus 1/4 cosine to the fourth x. And that is the antiderivative. So that's what we get here. So this becomes the integral from 0 to 2 pi. 1/4 times 8/3 is minus 2/3 cosine to the fourth phi, from phi equals 0 to phi equals pi over 4 d theta. So integral from 0 to 2 pi minus 2/3. So evaluating at pi over 4, cosine of pi over 4 is 1 over root 2. You take that to the fourth power, you square it, you get a half, fourth power, you get a quarter. So that's 1/4 minus at 0, you just get 1 d theta. So this whole thing is equal to minus 3/4 minus 2/3 times minus 3/4, so it's just positive a half. All right, so a half times 2 pi is just pi, right? So that's the volume of that snow cone, slightly different type of snow cone, and we did the triple integral of the function 1 over that region. Okay, so we'll have plenty more examples of this to do throughout the section. So we'll just end the lecture at this point and do more examples during our discussion.